Okay, so today 3A wraps up chapter 3. This is a thing called Newton's method. So Newton's method is designed to solve any equation as long as it's equal to 0. So you have some algebra experience with small questions like that, where quadratic equations like x squared, x's numbers, you've always gotten those equal to 0. You've tried to factor, you've solved them. You've been doing that since algebra 1. Algebra 2, we worked in, sometimes you couldn't factor, so you had to do the quadratic formula. We wrote a program in trig that does that, all of that. That's the type of equation we're talking about. In our old Algebra 2 days, this might be a distant blur, but I'm going to give you an Algebra 2 re-reminder seminar. You had a difficult time in your life of this because we learned this in quarantine at home. So how much of life from quarantine at home has stuck? That's a little bit uncertain, I think, in everybody's life from that 2020 year of chaos. Do you have any recollection in Algebra 2? It was like the last chapter we did. Anything we did when we were trying to solve stuff like that? All?
We like separated some stuff from the other. Like we would only do 3 parts at a time.
Vaguely remember that?
Yeah.
Okay, there's a thing called synthetic division. And synthetic division doesn't come into play today. I'm just trying to connect this to things that we do know and or a little reminder. For synthetic division, you copy the coefficients, and then you basically guess a number that you thought might work in this equation to make it 0. And it would have to be a number that could divide into 6. So pick a number that could divide into 6. 2. And then we hope for the best. The synthetic division process is to drop the 1, bottom level times this makes something, add down, 0 times that goes here, add down, multiply those is -10. The goal is to get 0. If we got 0, you picked the lucky winner. You didn't get 0, so you picked an unlucky loser. So then you go back to the drawing board and you guess another number other than 2. So go ahead, guess another number. 3. So we get 3, we drop the 1, times 3, add down, times 3, add down, times 3, jackpot. This was x cubed, so this is x squared. And then you go back to your other Algebra 1 bag of tricks. Factor if you can, quadratic if you can't. You know, this does factor x and x, plus 2 minus 1. This tells you 1's an answer. This tells you -2 is an answer. That told us 3 is an answer. We've got 3 answers. If your initial guess, if you had guessed -2 instead of +2, that would have been a hit. And then it would have just been a different problem that factored differently, but all roads will lead to this, this, and this, but we're reliant on making that lucky guess. Okay? One lucky guess gets you from x cubed to x squared, and x squared problems are manageable. If it was x to the 4th, you'd have to make 2 lucky guesses. If it was x to the 5th, which was the highest we did in Algebra 2, you had to make 3 lucky guesses. But that was like the scheme that we worked through. Vaguely familiar?
Yeah.
The problem with this is, what if this is like really, 3.62984, 1.37, and -2.918? You're never going to guess any of those. It's never going to happen. Or what if there were trig in that, or square roots in that, or weird powers or weird fractions, or there's a lot. This was pretty limited to only worked if we had whole number stuff, and only worked if we got answers that were like whole numbers, or we got some simple fractions like 3/2s and stuff. But we didn't have anything that was too off the wall. So math people aren't satisfied with that, so they want to develop a new scheme. So before we do that, what do you think about a giveaway of the problem that would lead you to expect that it might have 3 answers?
The third power.
Third power. Okay, so the power of the problem can be called the degree of the problem. So the degree of the problem always tells you how many answers are possible You don't always have to hit that number. An x cubed problem doesn't always have to have 3 answers, but that's the max that it could have. Sometimes you might only get one answer. Let's say we got the 3 here, and then this factored to x minus 3, x minus 3. Then you'd have gotten 3 and 3 in addition to you already had a 3, and there's only one answer for a setting like that. So you don't have to have 3 different answers, but that's the max that you can have. What we're going to do today to start our questions is graph this. Graph this will tell you how many answers there actually are. This is not representative necessarily of that. I wasn't trying to do it. If this is actually the graph of that, it's total blind lockout. But this graph does have 3 answers. There's a visual way we can look at this and go, this has to have 3 answers. Do you have any idea how visually this tells you there's 3 answers?
Every time it hits the x-axis.
X-axis touch points. So since this has 3 x-axis touch points, that gives us certainty that there are 3 answers because we can see that there are. It also would give us a like fair guess as to what those answers might be. Definitely one of the answers would be 0 for this graph. And then if I had some kind of scale on this, you know, we might have a guesstimate as to how far we were on the x-axis for those. Maybe this is like 4, and then that one would be like 10 based on the relative spacing therein. Question about that? Good with that concept so far?
Yeah.
Okay, so here's Newton's idea. Newton's idea is to use derivatives, meaning slopes, to do some tracing here. I'm going to make this be a little bit bendier of a bend, just to help me out to do what we had going on there. So slightly bendier thing. If you wanted to, let's say, find this point, you'd make a guess somewhere in that area. So, you know, if this were like 3 and this were 4, 5, we're probably a little closer to 4 than anything. So he might just make a guess of 4. If you plug 4 into the equation, you'd have to have an equation to make this work. Okay, so if you have an equation and you have a number that's at least in the neighborhood, like 4, if you plug in 4 as an x, it gives you a y. Like, I have an equation like this y equals, you know, if I plug in any x, it gives me a y. So he could come up with an x he wanted to guess. Plugging it in amounts to going like that and figuring out how high it is. At this point, you have a slope. The derivative gives you a slope of a tangent line, and now we just landed there. We just got closer. We could make this better if we just repeated the process. We could take this new thing, maybe that's like 3.7, I don't know. If you plug in 3.7, that amounts to just tracking straight up to get a y. And then there's a tangent line with a slope there, that's the derivative. And now we hit that point. Maybe that's 3.6, I don't know. Something that's getting closer and closer and closer to the answer. And now I need to quit drawing, because from where you're seeing and the video's recording, you couldn't even see what I'm doing anymore. But if you keep tracking straight up till you touch the curve, that's plugging in your guess. And then the derivative takes you diagonally closer and closer and closer until you're as close as you want to be. Does that make sense? Mm-hmm. If we had started with 3, we'd have still zoomed in on this, but through a different scheme. You know, if my guess was 3, I track to there, and then I follow the slope to land right about there again. I still land on basically that same spot. If I were trying to zoom in on this location, maybe I made a guess that's here. I track up, I follow the slope, and I hit there. That actually got farther. But if I track down, come in here, you know, that got farther. Sometimes weird things happen. If I track up and go diagonal, well now I just like bumped into that one by accident. So like sometimes weird stuff happens and you get the wrong answer. This must have been a little too far away from that to be a decent enough guess for that to track. Okay, but it amounts to track it vertically, then the derivative follows you diagonally, and your guesses get better as you go. That's the concept. Good? So here this is in rule form. This little weird subscript is a reference to your next, I'll say, guess. It's not like a guess anymore because it's getting better. But you're using one guess to get a better guess. And we're trying to get better. This, I guess we could refer to as like a first guess. And that truly is a guess. Okay, so we make a first guess, and then we're going to subtract a fraction where this is representative of the guess plugged into the original. That's the equivalent when we track straight up. This is the guess plugged into the derivative. That's the equivalent of every time I track diagonally. So we'll just need a guess to begin with. We'll need to plug that guess into the original. We'll need to plug that guess into a derivative. And if we do, the guess minus the result divided by the other result, we're going to get a better guess. And then you can repeat the process. Does that make sense? Yeah, to some degree. So the problems start off as every problem does in this chapter. It's the derivative chapter after all. So do the derivative. The derivative of x squared minus 2 is just 2x. Before we do anything else, or before you even did the derivative, it's an outstanding idea before you do anything to graph. Okay, because graphing is going to tell you both how many answers are we seeking. We're suspecting 2, because x squared. But it'll for sure confirm how many answers do we want and about how big they are. This question, the math is artificially easy. Like, you don't actually need this system to solve x squared minus 2 equals 0. We could do this with algebra 1 and algebra 2 skills, but I'm just trying to get off to a simple start. Okay. But to do a graph, if we graph x squared minus 2, do you remember, have a thought on what that would look like?
Would it be a u but down 2?
It is a u but down 2. So that would give you absolute confirmation that there's 2 answers, which we expect with x squared most of the time. And then if you graphed it on your calculator, it would be somewhere in between 1 and 2. You have the benefit of some nice technology in your hand there in the calculator. When I did this when I was a younger person, I'd probably make 1 my first guess. Okay, so I would have to go 1 squared minus 2 is what it is. 2 times 1 is what it is. 1 minus, this is the 2 divide, no, this was the negative 1 divided by, that would be the 2. The first plug-in is easy, but that usually gives you a kind of a weirder decimal. Then you have to go weirder decimal plugged into this, weirder decimal plugged into this, weirder decimal plugged into this, decimal minus decimal dividing decimal, and then your decimal gets weirder. And then that weirder thing has to go in. And every time you do it, the decimal gets like longer and weirder and stranger and like more bizarre. You have the ability on your calculator to not have to keep track of writing down what all your answers are. Like here, I went from 4 to 3, 7 to 3, 6. You don't have to write that down. You can just let the machine do this for you. So here's the way I would push the buttons on this. My first guess here would be ballpark like 1. So I would just, even though this seems weird, hit 1 and hit enter. It seems like too simple to be worth the step to do 1 and hit enter, but it's going to be worth it. That expressed this formula in terms of the answer buttons. So in this position, I'm going to go answer button minus. For this original formula, I'm going to go parentheses and call this answer squared minus 2. And then for this formula, for the bottom, I'm going to go 2 times answer. So go ahead and just push all those buttons and then I'll come along with you. So answer squared minus 2 divide teacher. Okay. Hit enter. 1.5? Okay. So if you were going up in the days that I grew up, I'd have to jot down 1.5, and then I'd have to go 1.5 plugged in there, probably jot that down. 1.5 plugged in here, jot that down. 1.5 minus the 1 divided by the other, and then jot that down. All you have to do is hit enter. Because it's again, all we're wanting to do is put the 1.5 in all the same slots, we just put the 1. And now it says 1.4166666666. Okay, so in my day, I would then have to sit there on the calculator and go 1.4166666666 squared minus 2, write it down. 2 times 1.6666, write that down. All you have to do is hit enter. And now it says 1.414 stuff. If you want to get better, hit enter again. If you want to get better, hit enter again. And at that point, I would stop. How do I know I can't get any better than that?
And it's not changing.
It's not changing anymore. It's repeating itself. And then I would just write down that whole thing. In the homework, they're going to tell you to go like 3 rounds. Ignore all that. We're just going to always go until it can't get any better and write it all down. So they had in mind, when they authored some of these questions, they were on the fringe of, these calculators existed, but people weren't quite sure how to use them when that book was first written. And so they were taking it easy on the people that they're thinking they'd have to keep writing down and plugging in and writing down and plugging in. We've got the power of the machine, just go till it repeats. So ignore anything where they say go 2 rounds or go 3 rounds. We'll just go as many rounds as we have to go till it repeats. Do you have a sense on why we're not completely done with that question, even though we did just get that 1.414 thing as an answer?
There's another answer.
There's another answer. So for this, you can absolutely judge from symmetry that if the positive 1.4 is an answer, so is the negative version. If you didn't have that kind of symmetry in your problem, what I would do is, to get this guess, go like -1 and hit enter as a different start point. And then do that second entry technique. Do the second entry thing so that this is back on your screen. And then go enter, 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 and go until it repeats, and it would give you the negative one. So on something like this, where there was no symmetry to this graph, and we have 3 answers to find, I would have guessed 4 or 3. You know, either guess 4 or 3. Create one of these things, and hit enter, 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 and then you've got that answer. Then go like whatever number that's close to and hit enter. Recall this, just hit the enter button. Each problem you should only have to enter the crazy formula all the way out once, and then it's just a matter of using the features. Well, yeah. So one more of those. Sometimes they give it to you in a slightly different format, where they say, when does this cross this? So f of x means the same thing as y. So if y equal this and y equal that, the transitive property tells you those have to equal each other. That equation isn't quite ready to do this method. You have a sense of why that can't do the method right this second?
It's not equal to 0.
It's not equal to 0. This thing only works if we're equal to 0. So x cubed minus x minus 1 equals 0. This could have up to 3 answers. Maybe fewer, definitely not more. To be sure, let's graph it and look and see what it looks like. I'm going to graph this on the calculator because I have no real sense of what this looks like. The x squared I knew was a u, but this, I don't have a clue. So we're going to go x to the third minus x minus 1. Button. And I don't know what I graphed previously here, but I need to zoom standard because I'm looking at a really weird thing right now. And we got lucky. because the graph has like a little hook there, but below the touch point, and then off it goes to the heavens there, and it's touching somewhere between 1 and 2. So the -1 here took our graph down just a touch, and it kept it from going and have that hook touch twice before it soared. This easily, a graph of this shape could easily get 3 touch points, but we ended up with 1 touch point. So celebrate those. That just cut our work by a third. Do the derivative. So derivative is 3x squared minus 1. And then it's basically time to push buttons. So you could either guess 1 or 2. I feel like it's closer to, you know what, I'm going to go 1.5. Just to speed it up a little bit. Like it's clearly between 1 and 2, so I'm going to go 1.5, hit enter. And then I'll go answer button minus. And then in parentheses, always do the original formula, just expressed with answer buttons. So answer button to the third, minus answer button, minus 1, all wrapped up in parentheses. Divide by. For the bottom, always do the derivative formula, but using the answer button. And again, all wrapped up in parentheses. 3 answer squared minus 1, wrap it up. And then I'll hit enter. And I show 1.34, 1.32, better 1.32, and then it repeats with 1.324717,957. That work for you?
Hold on.
You got it?
What was that?
1.324717,957.
What did you plug into the, like what was the formula?
So I did 1.5 and hit enter. And then I did answer button minus. And then in parentheses, I did this formula. But instead of answer button, I did, or instead of X's, I did answer button. So in parentheses, answer cubed minus answer minus 1. And then divide by. And then I did the derivative formula in parentheses, 3 answer squared minus 1. And then I just hit enter until I lost enter.
Okay. And then you got the 1.3247.
17957.
Okay.
That work?
Yeah.
Okay. The key thing by the time you take a quiz on this, you've got to know or have a feel for what the formula is. I mean, you don't have to memorize the formula verbatim and all the weird symbols, but you do need to understand it's always answer minus original dividing derivative somehow. I've had people get those flipped, and if you get those flipped, you'll know you got it flipped because like it won't work. It'll just go like crazy, and it won't. This you can see it's converging on an answer. It keeps getting better, better, better. You'd see it bouncing all over the world. Even if you do the right thing though, we saw that here. We got a little bit of bouncing there, but if you knew that you were going to get an answer around 0, when it did bounce to that answer, you would just be like, okay, something weird happened, I found the wrong one. Sometimes it does bounce in crazy directions if you get too close to a hump. You know, sometimes you're trying to find the thing over on this side of the hump, but it might bounce you and then you by accident are on the wrong side of the hump. And sometimes there's no recovery from that. You know, generally speaking, anything you guess from here forward should zoom in on that cross. And I would normally expect anything in between the valley or the peak and the valley, I would expect any number in here to start with should zoom in on the touch point, but it is a little unpredictable. You good? Hopefully the home audience is okay with that as well, and we can cut that video.